Right, this is our bonding summary video 3 now. So far in our first 2 videos we've looked at ionic bonds, how they're formed, and how the structure looks and the characteristics of the ionic substances. By characteristics I mean melting point or electrical conductivity. We've done covalent bonding. We've done some simple molecules here of hydrogen, methane, oxygen and carbon dioxide, exactly how those covalent bonds are formed. And what I want to look at in this video now is to start with the structure of a simple molecule, and then its physical properties. By that I mean, is its melting point high or low? Does it conduct electricity? Right, so to start with that. So, a nice simple example of a covalent substance, a simple molecular covalent substance, is this one here, methane. So if you watched last video, you can see how the bonding works to give every atom a full outer shell of electrons. But this molecule is tiny, infinitesimally tiny. So if we've got a lot of methane, how do those molecules interact? What does its structure look like? That's what I'm interested in now. So I've got this box here, and this box is in the structure row. So let's go over and do this. So this methane molecule here could be this methane molecule here. Carbon joined to 4 hydrogens. I'm just going to write C with 4 hydrogens around it and draw that in a ball like so. Okay. Now that methane molecule, could be next door to another methane molecule. Now methane is a gas at room temperature. It's the gas that comes out of the gas tap in your chemistry lab. It's the gas that powers your gas stove if you're piped into the mains at home. Okay, this gas comes out the bottom of the North Sea or other oil wells and things like that. Okay, so we've got lots of these small molecules. Okay, and it's a gas, so they're spaced out all over the place. Now, what we're interested in is, does it have a high melting point or a low melting point, I suppose? Well, we can understand that if we understand this structure. Okay, what we have here is methane molecules. Okay, now these methane molecules were formed by carbon sharing pairs of electrons with hydrogen. Okay, so what we have these molecules, and within these molecules there are strong covalent bonds. Strong covalent bonds. Okay, but between these molecules there is nothing. So I'm just going to put a dotted line between them. Okay. And these dotted lines, let's just label these up. There are very, and this is really important, very weak, I haven't really left myself enough room here, very weak forces of attraction. In other words, one molecule is not joined or attracted to another molecule. Yes, there's strong bonds within the molecule, but the forces of attraction between the molecules are weak. So let's do the melting point. The melting point, this is a gas at room temperature, so the melting point and boiling point are both low. Covalent substances generally have simple molecular, simple molecular. These are simple molecules. They're simple molecules because all the bonds in the molecule stop within the molecule. They don't go out of the molecule to other molecules. Okay, so a simple molecule is a smallish unit. I say smallish, but simple molecules could have, in some cases, I suppose, a couple of hundred atoms in. They're still small molecules. Okay, because atoms, of course, are so tiny. So simple molecules can be very big, I suppose, if you see them written out. But the bonds, what they have in common is the bonds stay within those molecules. So this is quite a small, simple molecule, this one, for example. Okay, so the melting point of these is low because, now, the standard wrong answer here, and this question gets asked all the time by examiners. Why? Because they know students will just give the wrong answer, so they don't have to think of a different question because they know they know they can separate those that know about chemistry from those that don't know about chemistry with this question. Why do simple molecules, simple molecular substances, have low melting points? Well, they have low melting points, and the wrong answer people give is because they have weak bonds. Okay, this is not true. The covalent bond is strong. The covalent bond is strong. So don't say they've got weak bonds. They have, the melting point is low because there are weak not bonds, not bonds. Weak, let's put it in capital letters. Forces of attraction between molecules. Okay. So if there's weak forces of attraction between molecules, only a little heat energy is needed to separate the molecules. I've gone out of my box there. My apologies. Hopefully you can read that, or if you can't read it, hopefully you understood it when I spoke it. Let's just read it through again. The melting point is low because there are weak forces of attraction between the molecules. Only a little heat energy is needed to separate the molecules. Okay, bit of a mouthful, but hopefully you understand it. Electrical conductivity. This is quite easy. Because the bond is formed by sharing of electrons, these molecules are not charged. So there's no charges. Okay, there are no charges. When we had ionic bonds, we had charged ions because the electron was transferred. There's no electron transfer here, it's sharing, so there's no charges. Now the other thing to see is all these electrons are locked up in bonding, so there's no free electrons. So it's very simple. No charged particles or free electrons. So if there's no charged particles or no free electrons, and if we remember, a current of electricity is a flow of charged particles. So we've got no charged particles and no free electrons, so doesn't conduct. Solubility in water. Well, much like ionic, I suppose. Some do, some do not. Some do not. And let's just leave it there. Some simple molecules do dissolve in water, so the smaller molecules tend to. Some of the bigger molecules, like oil molecules, they're simple molecules. Because they're bigger, they don't dissolve in water. I don't think we need to know too much more about that for GCSE. Right, so they are simple molecules. Now, having said that, there is another type. There is another type of molecule, and these are giant molecules. And giant molecules are massive. And the difference between a simple molecule and a giant molecule is the bonds in a giant molecule go throughout the entire molecule and only stop when the molecule gets to the end, when the large lump of it gets to the end. Graphite is quite a good one to draw and be able to see it because it is a little bit easier to draw. But there's two main examples of giant molecules, and they both are carbon-based. Okay, carbon's quite unusual as it can bond together in different ways. If you're extremely lucky, you can find a lump of diamonds. Now, carbon, as we saw up here, okay, this was a carbon atom in the centre of methane. Carbon has got an atomic number of 6, so it's got 2 electrons on the first shell and 1, 2, 3, 4 on the second shell. So to get a full outer shell of electrons, it forms 4 bonds, and you can see them there. 1 bond, 2 bonds, 3 bonds, 4 bonds. So carbon wants to form 4 bonds. And in carbon diamond, carbon does form 4 bonds, and it forms 4 bonds to itself. So there's a carbon, and it forms a bond, another bond to a carbon above it, another bond to a carbon beside it. Now, the carbon diamond is 3-dimensional. In other words, it's very difficult to draw on a flat piece of paper. So there will be a carbon sticking out of the piece of paper if I could draw it really well. So I'm going to do that with a bond that's getting thicker and thicker as it comes out towards me. And there'll be a carbon behind the piece of paper. So I'm going to draw that with a dotted line disappearing backwards like that. So carbon forms 4 bonds. But that's not where it stops. This carbon here also forms 4 bonds. Okay? Okay? And this carbon here also forms 4 bonds. This carbon here also forms 4 bonds. Okay, this carbon here also forms 4 bonds. And what you see, if we do this and it gets bigger and bigger and bigger, is we actually get 6-membered carbon rings. Okay, with every carbon forming 4 bonds, and it forms a 3-dimensional structure that goes on and on forever and ever. Carbon graphite, similar but slightly different. Okay, in carbon graphite, carbon doesn't form 4 bonds, it forms 3 bonds. And this actually is a 2-dimensional structure, so it's actually a lot easier to draw. Okay, it also forms 6-membered rings, but this time each carbon only forms 3 bonds. So if you look at that carbon there, it's forming 1, 2, 3 bonds. Okay, and we end up with this hexagonal flat structure that goes on forever and ever. And once you get a hang of drawing it, you can just draw it, and it's actually quite relaxing, to be honest. I always quite like drawing carbon graphite. It just goes on in these flat sheets. Not just one flat sheet, there's lots of flat sheets. And these flat sheets just sit above each other a little bit. They sit just out of sync, so this 6-membered ring here will just be out of sync with the 6-membered ring beneath it, like so. Now, and we end up like that, and we end up with a whole other flat sheet there. And then this the sheet beneath it is back in sync again, so that carbon there would be directly above a carbon here, forming the start of another 6-membered ring. You get the idea. That's not the whole thing though. Carbon graphite is quite special. Because carbon here is only forming 3 bonds, look, there's a carbon, it forms 1, 2, 3 bonds. Okay, because it only forms 3 bonds, and carbon wants to form 4 bonds, so that'll be 1, 2, 3 bonds. There's an electron kicking around down the bottom here that's not being used. Now that electron is not being used in bonding, sits between the layers. So it's kind of like bricks in the wall, and this electron here is the glue that's like the cement, I suppose. If that analogy suits for you. It doesn't glue it together as such, but these electrons do sit between the layers. Now these electrons sitting between the layers are what is called delocalized. Delocalized electrons. They're delocalized electrons. Means they are free to move, which makes graphite quite a useful substance, and we'll come to that in just a second. So next one, melting point is our next one. Well, what I said a moment ago, if we go back to simple molecules, is there was strong covalent bonds within the molecule. Okay, diamond here, there are 4 bonds holding every carbon, which means if we want to melt it, we have to break every single one of those strong bonds. So the melting point is very high, about 4,000 degrees. Incredibly high. Why? To melt it, you have to break 4 strong covalent bonds. Okay, and that's a very similar answer over here for carbon graphite. To melt this, we've got to break these 3 covalent bonds. That's also very high. Not quite as high as graphite, of course. Not quite as high as diamond. Because there's only 3 bonds here, there's 4. This is the highest melting point of any naturally occurring substance, actually. It's incredibly high. It also means diamond is incredibly strong, so it can be used for cutting tools. Okay, diamond-tipped drill bits. Why? Because it's so incredibly strong. Diamond is the hardest substance, naturally occurring substance known to man. It will scratch every other substance in existence because it is so incredibly strong. Okay, so that's why that's quite special. The melting point of this one also high. The other unique thing here, let's write it down here. It's not melting point, but let's put this in here. Okay, graphite can be used as a lubricant. Okay, let's explain that one. These layers of carbon atoms are not joined to each other, and they simply slide over one another. This is how a pencil works. The lead in a pencil is not lead, it's graphite. And as you scrape the pencil over the piece of paper, you scrape off one of these layers because they're not joined. And so graphite can be used as a lubricant. Electrical conductivity of diamond? No. For the same reason simple molecules didn't conduct, because there is no charged particles or free electrons. Graphite? Yes. Why? There are delocalized electrons. There are delocalized electrons that are free to move. And of course, neither of these are soluble. No and no. And that's finished.